In this video, we're going to talk about vectors and the connection between them and whether there exists a solution to a linear system of equations. So specifically what we're going to try to do is we're going to try to answer the question, if I'm given some vector, how do I determine if that vector can be written as a linear combination of some set of vectors? Or equivalently, how do I check if that vector is in the span of some set of vectors? Okay, so here's the context. First, let's suppose that we have a linear system with m equations and n variables. And this system has the following augmented matrix, which I've written out here below. So notice that this matrix has m rows all the way down to a sub m comma 1. This is the first entry in that mth row. And then there's n variables because to the left of this augmented bar, there are n columns. Okay, so what I want to do first is I want to introduce some new notation to express this augmented matrix a little bit more concisely now that we have the notion of vectors. So each of these columns we can think of as a column vector. So for example, this first column here I can think of as the vector a1. So I'm going to just write a1 with a vector on top of it to represent that whole column. The second column I'll call a2, and then dot 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 up until the last column to the left hand side of the augmented bar, which is an. And then I have my augmented bar, and then the column to the right of it, let's just call that b. So each of these vectors here is a column vector. So each of these is a column vector in Rm, because each of them has m entries. And I know that because my matrix here has m rows. Okay, so let's remember that everything to the left of the augmented bar, we had a term to refer to that. That was what's called the coefficient matrix. The coefficient matrix, and I'm going to call this A. So if I think of that whole thing as just being a matrix in and of itself, I can write this even more succinctly as just writing A to the left-hand side of the augmented bar, and then writing the vector B on the right-hand side. Okay, so what I want to do next is look at the connection between when a system like this, once I put it in augmented form, has a solution, the connection between that and linear combinations. Okay, so let's suppose that I have a vector x, which when I write it in terms of its entries is x1, x2, up until xn, and let's say that this is a solution of this augmented system. So whatever our system of linear equations is, when I put it in augmented form, I get some matrix A on the left and some vector B on the right. Okay, so what it means for this vector to be a solution of this system is when I plug in x1, x2, up until xn, whatever those numbers are, in the spot of the variables, it satisfies my equations. And I've written that underneath here. So this vector is a solution if and only if, notice I've plugged in x1 here for the first variable, x1, well, let's just write that better. Okay, so this is x1 plus, and then this should be an x1 as well. And then I've plugged in x2 for the second variable's location, so x2, and so on. That's what it means for this vector to be a solution. When I plug in the numbers x1 up until xn in the spot of the variables, it makes all the equations true. Okay, so now I have this system of equations with the x1 up until the xn plugged in. Let's rewrite this in vector form. So in vector form, what I will get is, notice that the first, if I sort of look at the first column here, I can make a vector out of that, factoring the x1 out. And if I do that, I'll get x1 times the vector a11, a21, dot dot dot, up until am1. If I do the same thing with the next column, I can factor out an x2 and then be left with a vector a12, a22, dot dot dot, up until am2. Continuing, so like this, I get plus dot 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 plus, and now for all the xn terms, I can form the vector with xn in front times the column vector a1n, a2n, dot dot dot, up until amn. So all I've done is I've just rewritten the left-hand side of this system of equations as these column vectors with these scalars in front of them, these x1, x2, all the way up until xn. And you guys might be noticing that, wait, this looks like a linear combination. And you're exactly right, it is a linear combination. Okay, and we'll get to that realization in just a sec. But, okay, so the right-hand side of the equation is still there. Let's write that as a column vector. b1, b2, up until bn. So the nice part about rewriting the system of equations in this vector form is just that it lets me capture it a little bit more succinctly. Now I only need to write one equal sign to sort of represent that, oh, all of these corresponding entries are equal. Okay, but what we've just realized is, like we were noticing, the left-hand side is a linear combination. It's a linear combination of these column vectors. So the first column vector, let me just call this a1. The next column vector, let me call that a2. Up until this last one, let me call that an. And then this vector with all these b's on the right-hand side, let's call that just b. Okay, so what this line here is saying is the vector b is a linear combination of the vectors a1 up until an. Okay, so that is what we will write down next. So this just basically says that b is a linear combination of a1 up until an. Okay, but there's an equivalent way of saying that. That's the same thing as saying that the vector b is in the span of a1, comma, up until an. Okay, so if I zoom out a little bit in terms of what we've just shown here, we've shown that if we want to determine if a vector b is a linear combination of the vectors a1 up until an, that's equivalent to checking if this augmented matrix, where I put the vectors a1 to an on the left-hand side of the augmented bar, and b on the right-hand side of the augmented bar, if I form that augmented matrix, checking if that has a solution. Okay, so I'll write this down to sort of sum everything up in just a minute or two, and then I'll do an example after that. But there's a little bit of notation I want to introduce first. So there's a notation that we're going to see a little bit more in detail in section 1.4 for how we can express this linear combination right here. Okay, so I want to introduce that notation to you guys now. So here is that notation. So let me scroll down, and now let's explain this. So this says if A is a matrix that has column vectors a1, a2, up until an, so this is an m by n matrix. So this x, we read that as the word by. So this notation means, so the m represents how many rows the matrix has. So we're assuming that it has m rows, and the n represents how many columns the matrix has, and it has n column vectors. So A is that matrix, and if x is the vector with entries x1, up until xn, so that has n entries, so this is a vector in Rn, then I want to define the product, so the multiplication of the matrix A with the vector x. So if I want to multiply a matrix with a vector, what that is defined to be equal to is we take the first column of A, so A1, multiply it by the first entry of x, x1, added to the second column of A, which is A2, so A2, plus the second entry of x, which would be, there would be an x2 here, so second entry of x, and I keep adding terms like that until I get to the last column of A, which is an, and I multiply it by the last entry of x, which is xn. So another way to say this is A times x, multiplying the matrix A times the vector x, gives us a linear combination of the columns of A, where the weights of the linear combination are the entries of x, or the x1, x2, up until xn. Those are the coefficients in this linear combination. All right, so now I want to summarize what we said before this, which is we drew a connection between when an augmented matrix has a solution and whether that vector b is a linear combination of the columns of A. So the following are going to be equivalent. I've written one thing down here. So this augmented system has a solution if and only if, and we just showed that this is equivalent to saying that b is a linear combination of the columns of A, which are A1, comma, dot, 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 up until AN. So if I want to check if B is a linear combination of the vectors A1 up until AN, form the augmented matrix and see if it has a solution. Another way to say this is, note this is the same as saying, I can rewrite this using the word span. This is the same as saying that B is in the span of the vectors A1, comma, dot, 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 comma, AN. All right. And the reason why I wanted to introduce this notation, which we'll see again in 1.4, is I wanted to be able to say another way to say this right now, which is, so if B is a linear combination of these vectors A1 up until AN, I can rewrite that in this A times X way. This is the same thing as saying that, oh, there is some set of weights that I can form into a vector X. That's going to make A times X equal B. So the way I write that is I say A times X equals B for some X, which is in Rn. And if it's a little bit unclear what I mean by this last portion right here, like this A times X equals B bit, don't worry too much about that because we'll see more in detail what this means in the next section. Okay. And then finally, just to review a little bit, when does an augmented matrix, when does that have a solution? So the way we verify that is if we row reduce it and put an echelon form, the echelon form has to have no row of the form where I get just a bunch of zeros on the left-hand side of the augmented bar and then something non-zero on the right. So there cannot be a row of this form. If there was, there is not a solution. There isn't a solution. Okay. So let's do an example. Okay, so example 3. This is continuing the numbering from the previous examples in this section. So I want to check if the vector 1, 2, 3 is in the span of these 3 vectors that I've written here. This is equivalent, so that's why I've written IE. In other words, this is asking, is the vector 1, 2, 3 a linear combination of those vectors? These are 2 ways of saying the same thing. Okay, so how do we do this? Let's talk about the solution. If I want to check if this vector is in the span of this other set of vectors, notice that's this right here. I have a statement like this that I'm trying to verify. What I need to do is I need to form the augmented matrix and check if that has a solution. So let's do that. So let's check if, and I need to write the augmented matrix. So the augmented matrix, I'm going to write the vectors like -1, 1, 2 on the left-hand side of the augmented bar. So I'm going to put those in real quick. Okay, so notice that I've put those other 2 vectors in here. And now let's put the augmented bar. And then I put the other vector, the 1, 2, 3, on the right-hand side of that augmented bar. So 1, 2, 3 on the other side. And I need to check if this system is, let's remember vocabulary, if this is consistent. And remember, consistent means, does this have a solution? Okay, so let's go ahead and do that. So to do this, we need to row reduce. Okay, so I've just recopied my augmented matrix here. So I have to row reduce this now. So it's totally fine that I have this -1 up here in this top, in this first entry of the first row. What I want to do is I want to sort of make the 1 below that and the 2 below that both become 0. So let's do that with the row operations. So I can make this 1 become a 0 if I take the first row and I add it to the second row. And then I insert that into the second row. I can make this 2 become a 0 if I multiply the first row by 2 and I add that to the third row and I insert that into the third row. Okay, so if I do that, the first row is going to stay the same as -1, 2, 1 augmented with 1. Let's close that bracket. So when I add the first row to the second row, I'll get, let's see, I'll get 0, 3, 3, and 3. That's kind of nice. Okay, and then for the next row, what will I get for the third row? So I have to multiply the first row by 2 and then add that to the third row. If I multiply by 2, I would get a negative 2 here. I would get a 4 there. I would get 2 here and 2 here. So I got to add these green numbers to the third row. So doing that, I would get 0, 4, 4, and 2 plus 3 is 5. Okay, so awesome. So we've done this. Okay, so next let's continue to row reduce. So what I want to do next is I just want to make this look a little bit nicer. One of the things that I notice is I have a negative 1 here, but to get it closer to fully reduced, I'd like to have a positive 1 there. So let's just multiply the first row by negative 1. Negative 1 times the first row, and just insert that into the first row. So I'm just scaling the first row by negative 1. The second row, I notice everything is a multiple of 3. So let's just let's just multiply the second row by 1/3. Second row multiplied by 1/3 and insert that into the second row. That's going to let me simplify. So the first row, everything changes signs. I'll get 1, negative 2, negative 1, augmented with negative 1. Second row gets divided by 3, so 0, 1, 1, 1. And the third row stays the same as 0, 4, 4, 5. Okay. All right. So next what I want to do to continue simplifying this is, I see a pivot here at the 1. I see a pivot here at the 1. But I need the 4 underneath that middle one to become a 0. So let's do that by doing negative 4 times row 2 added to row 3. And let's insert that into row 3. So if we do this, the first 2 rows stay the same. 1, negative 2, negative 1 augmented with negative 1. And then 0, 1, 1, 1. Those rows stay the same. But if I multiply the first row by negative 4 and add that to the third row, okay, so I'm going to trust that you guys can do this. Okay, and I think maybe I misspoke there. I meant to say I want to multiply the second row by negative 4, not the first row by negative 4. So multiply the second row by negative 4 and add it to the third. So if we do that, we will get 0, 0, 0, 1. Okay. And at this point, I don't need to reduce it any further. I see that I have a row of all zeros on the left of the augmented bar and something non-zero on the right because I have this 1. So right away, I can tell, sad face, this is inconsistent. This is not going to have any solutions. Inconsistent. And because it's inconsistent, that means my conclusion is the vector that I started off with, 1, 2, 3. This is not in the span of our set of 3 vectors. And I'm just going to write those down quickly. Okay, so those were our 3 vectors. So because we row reduced our system, got that it was inconsistent, there was no solution, that means our vector was not in the span of those column vectors. All right, so let's look at another example. Okay, I don't want to go too far down. Okay, because I want to have you guys try this for a couple minutes. So now, is the vector negative 9, 3, 10 in the span of these 2 vectors? So I'm just going to call the first one v1 and the second one v2. And I'll call this first vector b. So if yes, then find the weights x1 and x2 such that b equals x1 times v1 plus x2 times v2. Okay, so at this point, I want you to pause the video and try this for 2 minutes. So 4, 3, 2, 1, pause the video. Pause the video and try this for 2 minutes. Really try it. See if you guys can tackle this. Okay, so hopefully it's been about 2 minutes for you guys, just a few seconds for me. Okay, so I'm actually just going to show you guys all of the row reduction steps. The first thing I do is I take the vectors v1 and v2, write them as columns on the left-hand side of the augmented bar, put the vector b on the right-hand side, and if I row reduce it, at this point I know we're getting to be better and better at row reduction, I get to this step that we have here in the bottom right. And what I notice about this is an echelon form. So this echelon form doesn't have a problem. This echelon form, so EF for echelon form, EF, this EF has no row of the form where I just have a bunch of zeros on the left-hand side and then a non-zero thing on the right-hand side of the augmented bar. That's the type of thing that would be bad. That would give me no solution. So this doesn't have that, which means this system will have a solution. Okay, so now it's a matter of just writing what that solution is. So I have two ways to go about this. At this point, because I'm in echelon form, I could write my equations right now and then solve, but I would have to back substitute a little bit. So I'm going to reduce this all the way to reduced form, and that way I get to avoid having to back substitute. Okay, so to put it in reduced form, what I need to do is I still need to make this -2 a 0. So to do that, I will multiply the second row by 2 and add that to the first row and insert that into the first row. So doing that, my second and third rows stay the same. So I'll copy those down quickly. But now multiplying the second row by 2 and adding it to the first row, I'll get a 1 here, a 0 here. A -2 times 2 is a -4. Added to 9 gives me a 5. Okay, and at this point, now let's go ahead and convert these and write their corresponding equations. So for the first row, I'll have x1, there's no x2 term because of the 0, and then this equals 5. For the second row, I have no x1 term, but I do have one x2, or in other words, just x2. x2 equals -2. Okay, so these values, x1 and x2, these are, if I zoom out a little bit, these are these weights, x1 and x2. These are the weights in the linear combination. So thus, the vector that we began with, -9, 3, 10, this is 5 times the first column, -1, 1, 2, plus, sorry, I should write minus because I have a minus number, or a negative number, -2 times the second column, 2, 1, 0. So that's how I can write my vector b as a linear combination of those other vectors I was given. So let's box that whole thing. So that's another reason why this method for checking if a given vector like this b can be written in, as a linear combination of my other vectors is super nice. Because not only does this method tell me if it's possible or not, but it also tells me what those weights are going to be. Okay, so next I want to sum up one more key fact, which is, what if I want to check if my linear system has a solution for every single vector I could put on the right-hand side of the augmented bar? So what if this has a solution for every b on the right-hand side? Well, that's equivalent to saying that the span of the vectors in A, span of A1 up until AN, is all of Rm. It's equal to Rm. Basically, what we're saying is every single vector in Rm can be written as a linear combination of A1 up until AN. So these two statements are equivalent. But how do I check that? How do I check this in practice? So this is true if and only if our reduced matrix never, no matter what b is, never has a row of the form which would give me no solution. Never has a row of the form where I just have a bunch of zeros on the left of the bar and something non-zero on the right. But when would this happen? When would I never, no matter what b is, end up with a row like this? Well, I can guarantee I'll never end up with just a row of all zeros on the left of my augmented bar if my coefficient matrix, the coefficient matrix is what we call A, so what's on the left-hand side of the augmented bar, if that has a pivot in every row. Because if there's a pivot in every row, when I reduced it, I wouldn't have been able to end up with a row of all zeros on the left-hand side of my augmented bar at all. So in practice, this is how we check if a linear system has a solution for every vector b that I could have on the right-hand side. What I do is I reduce it and I see if my coefficient matrix has a pivot in every row. Okay, so let's do an example quickly where we check for this. Okay, so here is our example right here. So do the vectors 1, 2, 3, 1, 0, 1. and 2, -1, 1 span all of R3. So before I talk about the solution, what it means for these vectors to span all of R3 is no matter what vector in R3 I pick, I'm always going to be able to write that as a linear combination of these three vectors. In other words, I can form linear combinations of these three vectors to generate any vector in R3. I'm asking if that's possible. So based off of that key result that we just stated, what we do is we form a matrix where we put each of these things, each of these vectors as a column. So I'll do that quickly. Okay, so I've gone ahead and just inputted those vectors as columns. And I need to check if this, so I'm just focusing on the coefficient matrix. And check if there's a pivot, in each row. If there's a pivot in each row of this coefficient matrix, it doesn't even matter what's on the right-hand side of the augmented bar, it is going to span all of R3. It's going to have a solution no matter what vector I have on the other side, whatever B is. Okay, so to do this, I got to row reduce. Okay, so to row reduce, first I need to make this 2 become a 0 and this 3 become a 0. So I'm going to multiply the first row by -2 and add that to row 2 and insert that into row 2. Now let's multiply the first row by -3 and add that to the third row and insert that into the third row. Okay, so if I do this, my first row stays the same as 1, 1, 2. For the other two rows, I'm going to do this a little bit quickly, and I'm going to trust that you guys can check my computation. The second row will become 0, -2, -5. The third row will actually be the same, 0, -2, -5. And now I'm one quick additional row reduction away from reducing this into echelon form. Okay, the last two rows are the same, so I can subtract them to make one of them all zeros. So R3 minus R2, for example, and insert that into R3, into the third row, and this will zero out the third row for me. So the first two rows stay the same, so 0, -2, -5, but when I do the third row minus the second, the third becomes all zeros. And at this point, I see that the third row doesn't have a pivot. So since not every row has a pivot, this means that these columns, aka the vectors I started off with, these three vectors, don't span all of R3. In other words, I cannot write every vector in R3 as a linear combination of these three vectors.